Okay, welcome back to this session. This accompanies our topology optimization lecture. And here what we're going to be doing is exercising some topology optimization codes, which I've made available to you on Canvas. So all you need is MATLAB and these codes, and you can run everything that I'm showing you here in class. So you can play around a little bit with topology optimization yourself. I always think it's a lot of fun to play around with topology optimization. It's almost like magic whenever it happens, even though I've been doing it for quite some time. So in order to get this to run, the first thing you want to do is to go open up the file. You want to make sure you're in the right directory. And then you want to open up this file's top3D GUI. All right. And what I'm going to do is I'm going to run that file, and it's going to bring up a graphical user interface that you can see right here. Okay, I'm going to resize it just a little bit so I can see it a little bit better on my screen. All right, so what you can do here is if you go all the way down to the bottom, watch my cursor, and I'm going to click on Demo. And if I click on Demo, what it's going to do is it's going to set up a problem here. And up here in the upper left, you'll see, first of all, how many elements it's applied. And if you go look over here at outer bounds, NELX, NELY, and NELZ, you'll be able to see how many elements it's placed in there. And so in the X, there's 30. So along the X-axis, there's 30. In the Y-axis, which is sort of into the page, there's, or up and down, sorry, there's 10. And then in the Z-axis, which is into the page, there's 2. Okay, the other things it has done is it has specified Young's modulus as 1, Poisson's ratio is 0.3, and our penalization factor, remember, our p-value as 3. It's standard to put Young's modulus as 1 because everything's going to be non-dimensionalized anyway, so it doesn't matter as much what this value is. And Poisson's ratio, it's standard to put something like 0.3 because it's fairly representative of what a typical problem is. Over here on the right-hand side, you can see under optimization, the maximum number of iterations. Remember, I said there's an optimization algorithm, in this case, an MMA algorithm that's solving this problem in the background. And here, the most iterations it can take is 200, and it'll stop either when it hits those iterations or when the improvement in the objective function, which has to do with compliance, is less than this tolerance value. You can also tell it here whether you want to plot iterations or not. So you've got a check mark here. So I've got it checked so it will plot iterations so I can see every iteration how things are changing. Then let's look down in here at this design box. So we've got volume. This is our volume fraction, remember, at 0.3. And 0.3 is a 30%, means that up to 30% of this volume can be occupied by material. We've got R min, this is our radius for our filter to avoid checkerboard patterns. We've talked about that in our sister lecture to this on topology optimization. So this is a pretty typical value for that. And then if you were changing these values, you'd have to click apply to make sure those values get registered. Boundary conditions, supports. So UX, UY, UZ, those are displacements in X, Y, and Z. So those are all fixed. It's clicked something here called distribute. So it's going to fix all of the supports between the 0.000 and the 0.0102. So that means that everything on the back face between 000, which is that back corner, and 0.102, which is this corner that's up at the top left and closest to us, all of those degrees of freedom are going to be fixed. So no movement in the X, Y, or Z. All right. If you changed one of these, you'd have to click apply to get them to register. And then finally, there are loads. So you can put a load in the X, the Y, or the Z direction. They've chosen to put one in the Y. The minus means it's pointing down. This case, they've applied it to a single point, individual, as opposed to distributing it over a surface. And that individual point is at a distance of x1 equals 30. So the end of the domain at y equal 5, which is halfway up, and at z equal 1, which is halfway through the depth of the part. So the load is actually being applied right here in the midsection, and then that arrow points down from there. Again, if we had changed anything here, we'd have to click apply. So the next thing I'm going to do is click run. And when I click run, it's going to solve this. And so it's going to place material in the domain selectively, only in the places where it makes sense and it helps support this load. Remember, you can only have a volume fraction of 30% because that's what we told it. And these colors indicate how dense the material is. So a really dark color here means that the density is close to 1. A gray color here means that the density is somewhere less than 1. And if it's completely white, then the density is really small. Down here in this plot control box, there's a cutoff value here. And so this cutoff value is right now set at 0.5, which means it displays only elements with densities greater than 0.5. We can change that value, so we can move it all the way to 0. And here you can see it's showing us all of the elements, right? And so the white ones here are void. They're not solid at all. Their densities are at 0. The black ones have densities that are approximately 1. And then all the dark gray and light gray elements have densities that are somewhere between 1 and 0. So as we change that cutoff value, right, we can see some of those elements disappear because their densities aren't large enough to appear, right? It doesn't look like this is quite converged because I'd probably like to see, for example, an element right here connecting this last X to get it to run. All right, so let's try a different problem here, and we can play around with this a lot. So let's try, we've got in the X direction 30 elements. Let's try a slightly different shape to this. Let's try 5 elements in the Y and 5 elements in the Z. We'll keep everything else the same. That seems fine. And I'll apply this new, actually I'm going to close this, right? And I'm going to open it again because sometimes we have a little bit of trouble changing things midstream. The GUI is not perfect, all right? So I'm going to open the GUI again, and I'm going to change this problem a little bit. So let's have 30 in the X, and let's just change the proportions, and let's do 5 in the Y and 5 in the Z. We'll keep our volume fraction the same, our radius the same, and let's apply it. Okay, now we can see we've got something different, right? It's not so tall and slim. It's got the same depth in the Z as it has height in the Y, and it's 30 units long. All right, let's support on UX and Y. Let's do a distributed support again on the left-hand face. So everything from 0, 0, 0 to 0, 5, 5. So everything here from this back corner all the way up to this corner here on this left-hand face is all going to be fully supported, right? So we're going to apply there. Whoops, I forgot. All right, let's try this again. Let's do UX, UY, UZ from 0, 0, 0 to 0, 5, 5, right? And let's apply that. All right, now we have the back, the fully left-hand face, all the way to the left-hand side. The whole thing is supported, fully supported. So no displacements back there. And then let's apply a load. We can do a downward load again if we'd like. But how about, in this case, we could do a distributed load if you like, instead of a point load. So let's distribute that load from, say, 35, 0 to 35, 5. So instead of applying a point load, what we're actually going to be doing is we're applying a load all the way along that top edge, right, on the right-hand side, from 35, 0 to 35, 5. And that last dimension is the Z, so from front to back. All right, so we've applied all these things. Now we can run it and we can see it work, right? And see where it's applying material. So this design is going to look a little bit different because it's instead of applying a load at the midpoint of the beam, it's actually trying to apply a load all the way across the top edge of the beam. So the design is going to look a little bit different, right? So it's iterating, it's trying to decide where to put material, and it has now converged. I want to look at this a little bit and see, you can kind of turn it around, and you can see where material is and where it's not, and you can see it's kind of judiciously decided to put material in certain locations. We could try to run it again if you like. We could, for example, apply a larger volume fraction. We could apply that, take a look and run it again. And so now it's going to have the opportunity to put more material in there, right? Fill half of the space with material as opposed to just 30%. And we can see it much, much darker, much, much more material being utilized in there. Okay, so it's iterating, it's converging, and all of this is happening actually on my laptop. So you don't need a particularly powerful computer to get this done. So we can look now, we can see that this design has a lot more material in it, and then you can see it's kind of focused on the outer edges there, in the positive, the front face and the back space, and there's a lot of empty space inside to try to make best use of that 50% volume fraction that it has to use. So one thing I will tell you is that as you add more elements, so if we go up here to this design domain and the outer bounds, the elements, right now we have 30 by 5 by 5. If we try to add more elements to that, then it will get much more computationally expensive. So you want to be kind of careful about doing that. If you suddenly sit down and you try to do 1,000 by 1,000 by 1,000 elements, it's going to be really difficult for you to do that on your laptop. So just be careful about that. Start with small size domains. And again, hopefully this makes sense in terms of the numbers of elements. You can see 30 in the X, 5 in the Z, 5 in the Y. So we actually have 5 times 5 is 25 times 30, which is 750. There are 750 individual elements in here, and it's still converging really, really quickly on my laptop. You also might want to play around with the loads a little bit. I gave you a couple of examples here, but you need to get kind of used to the coordinate system so that you can apply loads the way you want. And individual just means it's going to be with supports or loads. Individual just means it's going to be applied at a single point, and distribute means that it's going to be applied all throughout that range of values that you've given to the right. So there's also another capability over here that you can use as well, and it'll convert your final design to an STL file. So there's a lot of ways to do it, but the quickest way to get it done is to go into this file called Top3D, which is something that's run by this Top3D GUI file. And you go into, say, line 112 is a good one to go in and hit a breakpoint, right? And then you go back to the GUI file and you run it again, right? And we're going to let it run and converge all the way. Let's see, hold on, let me close this out first. Close it out, right? And then we're going to run that GUI again, right? I'm just going to use the demo problem that came with it for just as an example. And let's run it. Then we're waiting for it to converge. And then because I put a breakpoint here at 112, it's just going to pause there. And then I can see my whole workspace over here on the right-hand side, right? And I can save my workspace if I like. And I've gone ahead and done that over here. I have a workspace over here called sample.workspace.mat. And then what I can do is I can run a different algorithm called Top3D STL v3. All right. So I'm going to go ahead and run that. I'm going to run that from the command line, and I'm going to do Top3D STL v3, and then I'm going to give it a name for the STL file, right? Okay. And then I'm going to have it call something called xphys, which is the variable in the workspace that records all of the element densities. And so what this algorithm is going to do is it's going to take all of those and it's going to convert them into an STL file that you can see. So here you can see I'm going to go back to my GUI and I can see the STL file that has been generated that would produce the part that I wanted, right? And you can actually see the triangles right there. And it's been saved in an STL file called example STL, right? So I could always go back to the original folder in which I found that STL file, and I could use whatever STL viewer I like to take a look at that. So that'd be one way to convert it to STL and to potentially print it, modify it, and print it. Okay. So play around with this a little bit. I think you'll find it very useful and very interesting to be able to get a little bit of topology optimization experience really easily. You'll find all these files on Canvas. Good luck.